Welcome to this coding walkthrough. Today, we'll explore problem number 759, employee free time. This problem focuses on finding gaps in schedules where all employees are free, using interval manipulation. Let's dive in and break it down step by step. In this problem, we are tasked with identifying the free time intervals that are shared among all employees in a company. Each employee's schedule is represented as a list of time intervals during which they are working. These intervals are non-overlapping and sorted by their start time. For example, an interval like 1, 3 means the employee is working from time 1 up to, but not including, time 3. The input to the problem is a list called schedule, where each element corresponds to the list of intervals for a specific employee. Our goal is to process these schedules and return a list of intervals representing the periods when no employee is working, sorted in ascending order. This gives us the common free time shared by all employees. The intervals in the output are also represented as start and end, where start and end are integers denoting the beginning and the end of the free time period. Let's look at an example. Suppose the input is schedule equals 1, 2, 5, 6, 1, 3, 4, 10. Here, we have 3 employees with different working schedules. Employee 1 works during 1, 2, and 5, 6. Employee 2 works during 1, 3, and Employee 3 works during 4, 10. To find the common free time, we need to identify the intervals during which none of the employees are working. In this case, the result is 3, 4. This means that the only shared free time across all 3 employees is between time 3 and time 4. The explanation highlights how we derive this by understanding the overlapping intervals and determining when no one is working. Here's another example to further clarify. If the input is schedule equals 1, 3, 6, 7, 2, 4, 2, 5, 9, 12, we again analyze the working intervals for each employee. Employee 1 works during 1, 3, and 6, 7. Employee 2 works during 2, 4, and Employee 3 works during 2, 5, and 9, 12. When we calculate the common free time, we find that the shared free time intervals are 5, 6, 7, 9. This means that all employees are free from time 5 to 6 and again from time 7 to 9. These results are sorted in ascending order, as required by the problem. Now, let's consider the constraints and edge cases. The number of employees, schedule.length, can range from 1 to 50, and each employee can have up to 50 working intervals. The start and end times for these intervals are positive integers, with start always less than end, and each employee's schedule is already sorted. Some important edge cases include, first, if there is only one employee, there will be no shared free time since there are no other schedules to compare with. Second, if the working hours of all employees overlap completely, the output should be an empty list as there is no common free time. Lastly, for extremely large intervals, such as from 0 to 10 to the power of 8, the solution must be efficient in terms of time and memory usage. These considerations are crucial for ensuring that the implementation works correctly under all scenarios. To tackle the problem of finding employee free time, one intuitive approach is the brute force method. Here, the idea is to combine all the schedules into a single list of intervals and then identify the gaps between these intervals. The process involves several steps. First, we flatten all the employee schedules into a single list of intervals. Next, we sort this list by the start time of each interval. After sorting, we merge any overlapping intervals to create a consolidated schedule. Finally, we traverse through the merged intervals to find any gaps, which represent the free time. While this method is straightforward and easy to grasp, it has its trade-offs. Sorting the intervals takes n log n time, where n is the total number of intervals, and merging the intervals adds an additional n step. This results in an overall time complexity of n log n, with space complexity of n, to store the flattened list of intervals. Now, while the brute force approach is simple, it does have limitations, particularly for very large inputs. Sorting dominates the time complexity, making it less efficient for scenarios with a high number of intervals. An optimized approach, which leverages a min heap, addresses these inefficiencies. This strategy prioritizes intervals dynamically instead of merging all of them upfront. The process begins by pushing the first interval of each employee into a min heap, ordered by their start time. The heap allows us to always extract the earliest interval. As we process each interval, we maintain a current end time to track the end of the last merged interval. If the next interval starts after this current end time, the gap between the two is recorded as free time. After processing an interval, the next interval from the same employee is added to the heap, if available. This continues until the heap is empty, ensuring that we process each interval efficiently while identifying all gaps. When analyzing the complexity of the min-heap approach, the efficiency becomes clear. Heap operations, such as inserting or removing an element, take O log k, where k is the number of employees. Since each interval is processed exactly once, the total time complexity of this approach is O n log k, where n is the total number of intervals. This is a significant improvement over the O n log n complexity of the brute force method, particularly when the number of employees, k, is much smaller than the total number of intervals, n. The space complexity is also reduced to O k, as we only store k intervals in the heap at any given time. While this method requires a bit more effort to implement due to heap management, its efficiency makes it the preferred choice for larger datasets or scenarios where performance is critical. The optimized approach using a min-heap was selected as the preferred strategy for solving this problem. This decision was based on several factors. Firstly, its time complexity of O n log k offers a clear advantage over the brute force method, especially when the number of employees, k, is small compared to the total number of intervals, and additionally, the heap-based approach is more memory efficient since it avoids creating a large, flattened list of intervals. By dynamically processing the intervals, this method is also well suited for real-time or streaming data scenarios. The core insight here is recognizing that we do not need to explicitly merge all intervals. Instead, we can track overlaps and identify gaps dynamically using the heap. This realization simplifies the problem while maintaining scalability and clarity, making the heap-based strategy both practical and efficient for solving employee free time on LeetCode. To solve the employee free time problem, we need to determine the intervals during which all employees are available. The first step in our brute force approach is to flatten all the schedules. This means consolidating all the individual employee schedules into a single list of intervals. For example, if we have the schedules 1, 3, 6, 7, 2, 4, and 2, 5, 9, 12, we combine these into one unified list, 1, 3, 6, 7, 2, 4, 2, 5, 9, 12. This gives us a comprehensive view of all the busy intervals across employees, which is essential for the subsequent steps of the algorithm. Next, the combined list of intervals needs to be sorted by their start times. If two intervals share the same start time, we sort them by their end times. For example, the unsorted list 1, 3, 6, 7, 2, 4, 2, 5, 9, 12 becomes 1, 3, 2, 4, 2, 5, 6, 7, 9, 12 after sorting. Sorting ensures that we process the intervals sequentially, which simplifies the task of identifying overlaps. Once sorted, we merge any overlapping or adjacent intervals. Starting with the first interval, we compare it to the next one, and if they overlap, we merge them. For instance, 1, 3, and 2, 4 merge into 1, 4, and with 2, 5, it further consolidates to 1, 5. This process continues, yielding a final merged list like 1, 5, 6, 7, 9, 12. This step reduces the complexity of the problem by consolidating busy intervals and creating distinct gaps between them. With the merged intervals, we can now identify the free time intervals. To do this, we traverse the merged list and find the gaps between the end of one interval and the start of the next. For example, given the merged intervals 1, 5, 6, 7, 9, 12, the gaps are between 5 and 6, and between 7 and 9. These gaps, 5, 6, and 7, 9, represent the time when all employees are free. Finally, we output these free time intervals as the result. In this case, the output would be 5, 6, 7, 9. This step highlights the free intervals that meet the problem's requirements. There are a few key insights to keep in mind. First, sorting the intervals is a crucial step because it ensures that we process them sequentially, making it easier to identify overlaps and gaps. Second, merging overlapping intervals simplifies the dataset by reducing it to distinct blocks of busy time, which directly highlights the free time intervals. Additionally, we must handle edge cases, such as when there is only one employee's schedule, where the free time is simply the complement of their busy intervals. If there are no overlapping intervals, all gaps between intervals are free time. On the other hand, if all schedules fully overlap, the result may be an empty list of free intervals. These insights help us understand the broader implications of the algorithm. Finally, let's discuss the data structures and complexity. The input is a list of lists of intervals, which models each employee's schedule. We create an intermediate flattened list of intervals, for example, 1, 3, 6, 7, 2, 4, 2, 5, 9, 12, and then a merged list, such as 1, 5, 6, 7, 9, 12. The output is the list of free intervals, like 5, 6, 7, 9. Key operations include flattening the schedules, which takes O, n, where n is the total number of intervals. Sorting the intervals as O, n log n, and merging them as O, n, since we traverse the list once. Finding gaps takes O, m, where m is the number of merged intervals. Overall, the algorithm is dominated by the sorting step, giving it a time complexity of O, n log n. This makes it efficient for scenarios with a manageable number of intervals. This solution addresses LeetCode problem number 759, employee free time. The input is a list of employees' schedules, where each schedule contains intervals representing an employee's busy times. The goal is to find the common free intervals shared across all employees. ### explanation of the code. 1. Input parsing asterisk. The input is a list of schedule lists. Each schedule contains busy intervals for an employee. We first flatten all these intervals into a single list using a nested list comprehension. This allows us to work with all intervals collectively, ignoring which employee they belong to. 2. Sorting intervals asterisk. The combined list of intervals is sorted by their start times. This ensures that we can process them sequentially and merge overlapping intervals effectively. The sorting is achieved with the sort method, using the start attribute as the key. 3. Merging overlapping intervals asterisk. As we iterate through the sorted intervals, we check whether the current interval overlaps with the last interval in the merged list, merged_intervals. If there's no overlap, the interval is added to the merged list. If they overlap, we merge them by updating the end time of the last interval in merged_intervals to the maximum end time of the two intervals. 4. Finding free time asterisk. Once we have the merged intervals, representing the total busy periods, the free times are simply the gaps between these intervals. We iterate through consecutive merged intervals and record the intervals between the end of one interval and the start of the next. 5. Output asterisk. The function returns the list of free time intervals. These intervals represent the periods when all employees are simultaneously free. ### complexity analysis. Time complexity asterisk. Flattening the schedules takes O, n, where n is the total number of intervals across all employees. Sorting the intervals takes O, n log n. Merging intervals and finding gaps is O, n. Overall complexity, O, n log n. Space complexity asterisk. The space used is primarily for storing the combined intervals and the merged intervals, which is O, n. This implementation is efficient and handles edge cases, such as no free time or all employees having disjoint schedules. Here, we start by defining an interval class to represent time intervals with a start and end point. This simple class will help us manage and manipulate intervals throughout the solution. Next, in the solution class, we implement the employee free time method, which takes a list of employee schedules as input. Each employee's schedule is a list of time intervals during which they are busy. The first step in this method is to flatten the input. We combine all the intervals from all employees into a single list, making it easier to work with the data as a whole. Once we have this combined list, we sort it based on the start time of each interval. Sorting ensures that we process intervals in chronological order, which is crucial for merging overlapping intervals efficiently. Finally, we create a merged intervals list to store the consolidated busy periods. As we iterate through the sorted intervals, we check whether the current interval overlaps with the last interval in the merged intervals list. If there's no overlap, we add the current interval to merged intervals, indicating that it represents a distinct busy period. However, if the current interval overlaps with the last interval in merged intervals, we merge them by updating the end time of the last interval to the maximum of the two overlapping intervals. This ensures that we consolidate all overlapping or adjacent busy periods into a single interval, making the data cleaner and easier to work with. After building the merged intervals list, we proceed to identify the free times. Free time is essentially the gap between consecutive merged intervals. To find these gaps, we iterate through merged intervals, starting from the second interval. For each pair of consecutive intervals, we calculate the gap by taking the end time of the earlier interval and the start time of the later interval. If a gap exists, we create a new interval object representing this free time and add it to the free times list. Once all gaps have been identified, the free times list is returned as the result, containing all the intervals when no employee is busy. Here, we start with a simple example where the input consists of overlapping employee schedules. First, we flatten the input to create a single list of intervals: 1, 3, 6, 7, 2, 4, 2, 5, 9, 12. Next, we sort these intervals by their start times. After sorting, the intervals become 1, 3, 2, 4, 2, 5, 6, 7, 9, 12. With the intervals sorted, we can begin merging any overlapping intervals. Starting with the first interval, 1, 3, we compare it with 2, 4, which overlaps, so we merge them into 1, 4. Then, we compare 1, 4 with 2, 5, which also overlaps, resulting in 1, 5. After merging the first three intervals, we move to 6, 7, which does not overlap with 1, 5, so we add it as a separate interval. Similarly, 9, 12 does not overlap with 6, 7, so we add it as well. This gives us the merged intervals 1, 5, 6, 7, 9, 12. Now, to find the free times, we look for gaps between consecutive intervals. The gap between 1, 5 and 6, 7 is 5, 6, and the gap between 6, 7 and 9, 12 is 7, 9. Thus, the free times are 5, 6, 7, 9. In this second example, the schedules do not overlap. After flattening the input, we get the intervals 1, 2, 5, 6, 3, 4, 7, 8. Sorting these intervals by their start times results in 1, 2, 3, 4, 5, 6, 7, 8. Because the intervals do not overlap, there is no need to merge them. We simply retain all four intervals as they are: 1, 2, 3, 4, 5, 6, 7, 8. With the merged intervals unchanged, we can now identify the free times. The gap between 1, 2, and 3, 4 is 2, 3, the gap between 3, 4, and 5, 6 is 4, 5, and the gap between 5, 6, and 7, 8 is 6, 7. These gaps give us the free times 2, 3, 4, 5, 6, 7. In the final example, all schedules are fully overlapping. Flattening the input gives us 1, 10, 2, 3, 4, 8, 6, 9. Sorting these intervals by their start times results in the same list, as they are already sorted. When merging, we start with 1, 10. The other intervals, 2, 3, 4, 8, and 6, 9, are all fully contained within 1, 10, so the result of merging is simply 1, 10. Since there are no gaps between intervals, there are no free times. The result is an empty list. To analyze the time complexity of the solution, we can break it down into three main parts. First, we combine all the intervals from the given employee schedules into a single list. This is done using a nested list comprehension, where we iterate through every employee and their respective intervals. If there are k employees and each has an average of m intervals, the total number of intervals becomes n equals k asterisk m. This step takes n time, as we are simply iterating through all intervals. Next, after flattening the list, we sort all intervals by their start times using Python's built-in sort function with a lambda key. Since sorting has a time complexity of n log n, this becomes the most computationally intensive step. Finally, we merge overlapping intervals. This process involves iterating over the sorted list once, checking and potentially modifying the last merged interval. As this iteration is linear, it contributes n time. Each of these steps contributes to the overall efficiency of the solution. In the next step, we calculate the free time intervals by iterating through the merged intervals and identifying the gaps between them. This step is also linear with respect to the number of merged intervals, which is at most n. Therefore, the time complexity for this step is O, n. When we combine all these steps, flattening, sorting, merging, and finding free time intervals, the overall time complexity becomes O, n plus n log n plus n plus n, which simplifies to O, n log n. Now, for the space complexity, we start by considering the flattened list of intervals. This list stores all n intervals, requiring O, n, space. Then, we have the merged intervals list, which stores the non-overlapping intervals after merging. In the worst case, where all intervals are disjoint, this still requires O, n, space. Additionally, we account for the free time intervals list, which stores the gaps between the merged intervals. In the worst case, where all intervals are disjoint, there could be up to n1 gaps, requiring O, n, space. Sorting the intervals may also involve some additional memory overhead, depending on the sorting algorithm used. Python's timsort, for instance, performs in-place sorting, which means it has an overhead of O1 for space. When we combine all these factors, the total space complexity is dominated by the space used for the flattened list, the merged intervals, and the free time intervals. This results in an overall space complexity of O, n. When comparing the optimized solution to a brute force approach, the efficiency improvement becomes clear. In a naive method, we would check every pair of intervals across all employees to find overlaps and gaps. This would involve iterating over all intervals for each employee, resulting in a time complexity of O, n superscript 2. By contrast, the provided solution first sorts the intervals, reducing the complexity to O, n log n. The merging and gap finding steps are linear, which makes this approach significantly more efficient. Even in the best-case scenario, where the intervals are already sorted and non-overlapping, the sorting step still takes O, n log n, so the overall complexity remains the same. For average and worst-case scenarios, the time complexity does not change, as sorting and merging are always required, ensuring the complexity stays at O, n log n. Mathematically, the sorting step dominates the time complexity because it involves O, n log n, operations, which grow faster than the linear operations for merging and calculating free time intervals. This is why the overall time complexity is dictated by the sorting step. On the space side, the solution is efficient because it uses space proportionate to the input size. Beyond the input intervals, the only additional data structures are the merged intervals and the free time intervals lists, both of which require O, n, space. With these considerations, the optimized solution is both time and space efficient, making it well suited for handling large input sizes, especially when compared to the naive approach. When working on problems like employee free time, one of the most common mistakes is failing to sort the intervals properly. Sorting is a crucial first step because it ensures that all intervals are in the correct order for merging. If you skip this step, you risk missing critical gaps or incorrectly merging intervals, which can lead to completely wrong results. Another frequent oversight is neglecting edge cases. For instance, you need to handle scenarios where employees have empty schedules, or where intervals span multiple employees in touch but don't overlap, such as 1, 2, and 2, 3. These cases require careful logic to avoid returning incorrect solutions. Additionally, errors often arise during the merging process itself. If you don't update your pointer or index correctly while merging, you might skip intervals or fail to detect gaps properly. Finally, inefficiencies can creep in when merging is done with nested loops or by repeatedly sorting intervals. To achieve optimal performance, aim for an O, n log n, solution by sorting once and then iterating through the intervals in a single pass. Another common pitfall is confusing start and end points during the merging process. It's important to understand whether the problem requires comparing start times, end times, or a combination of both, depending on the specific requirements. Misinterpreting this can lead to logic errors that derail your solution. Now, when you're solving this problem during an interview, it's helpful to recognize the underlying patterns. This challenge is part of a broader class of scheduling problems that revolve around sorting intervals and performing a linear traversal. Make sure to highlight your understanding of these patterns to the interviewer. You should also ask clarifying questions, like how to handle edge cases such as touching intervals or empty schedules, as this demonstrates attention to detail. In terms of complexity, you should aim for an O (n log n) solution, which is often the optimal approach due to the sorting step followed by a linear pass. Lastly, clear communication is key. Walk through the sorting and merging process step by step, and if possible, use diagrams to visually explain how intervals overlap and where gaps exist. This can make your thought process more transparent and easier to follow. This problem is closely related to several other interval-based challenges, which makes it a valuable addition to your problem-solving toolkit. For example, LeetCode 56, merge intervals, involves combining overlapping intervals, a concept that shares much of the same logic. Similarly, the employee free time problem itself focuses on identifying gaps between intervals rather than merging them, but the underlying techniques are comparable. LeetCode 252, meeting rooms, is another related problem where you determine if a person can attend all meetings based on whether intervals overlap. Finally, LeetCode 253, meeting rooms 2, takes this concept further by asking for the minimum number of meeting rooms required, which is a variation of interval scheduling. These problems collectively reinforce the importance of sorting, merging, and efficiently managing intervals, so practicing them will deepen your understanding of these techniques and prepare you for a variety of scheduling-related challenges. There are also alternative approaches to solving this problem, each with its own trade-offs. The brute force approach involves combining all intervals into a single list, sorting it, and then detecting gaps. While this method is straightforward and intuitive, it's not efficient for large inputs, as it can have a higher constant factor and, in some implementations, degrade to O (n squared) performance. Another approach is to use a heap-based method. By maintaining a min-heap to track the earliest ending interval, you can merge intervals and detect gaps efficiently. This method is especially useful in dynamic scenarios where intervals are frequently updated, but it does come with added implementation complexity. Finally, there's the sweep line algorithm, which treats interval start and end points as distinct events. By sorting these events and using a counter to track overlaps, this approach achieves an efficient O (n log n) complexity. However, it requires careful handling to differentiate between start and end events. Each of these methods has its advantages, so understanding their trade-offs helps you choose the most effective solution for different variations of the problem. Great job following along. To summarize, this problem taught us how to handle interval merging and identify gaps effectively. Remember the importance of sorting and optimizing for time and space complexity. Thanks for watching, and don't forget to like, subscribe, and keep coding. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!